Hey Charles, how's it going?
It's going pretty well, Michael. How are things going with you?
Good. I'm excited to tell you about neural networks today. You may be familiar with neural networks because you have one in your head.
I do?
Well, yeah, I mean you have a network of neurons, like you know neurons, like brain cells. I'll draw you one.
Okay.
So this is my attempt at drawing a nerve cell, a neuron, and you've got billions and billions of these inside your head, and they have most of them have a pretty similar structure. That there's the kind of the main part of the cell called the cell body, and then there's this thing called an axon, which kind of is like a wire going forward to a set of synapses, which are kind of little gaps between this neuron and some other neuron. And what happens is information, spike trains, woo woo, travel down the axon. When the cell body fires, it has an electrical impulse. It travels down the axon and then causes, across these synapses, excitation to occur on other neurons, which themselves can fire, again, by setting out spike trains. And so they're very much a kind of a computational unit, and they're very, very complicated. To a first approximation, as is often true of first approximations, they're very simple, sort of by definition of first approximation. So what in the field of artificial neural networks, we have kind of a cartoonish version of the neuron and networks of neurons, and we actually put them together to compute various things. And one of the nice things about the way that they're set up is that they can be tuned or changed so that they fire under different conditions and therefore compute different things. And they can be trained through a learning process. So that's what we're going to talk through if you haven't heard about this before.
Okay.
So we can replace this sort of detailed version of a neuron with a very abstracted away kind of notion of a neuron. And here's how it's going to work. Is we're going to have inputs that are kind of, think of them as firing rates or the strength of inputs, x1, x2, x3 in this case. Those are multiplied by weights, W1, W2, W3, correspondingly. And so the weights kind of turn up the gain or the sensitivity of the neuron, this unit, to each of the inputs respectively. Then what we're going to do is we're going to sum them up. So we're going to sum over all the inputs the strength of the input times the weight. And that's going to be the activation. Then we're going to ask, is that greater than or equal to the firing threshold? And if it is, then we're going to say the output is 1. And if it's not, we're going to say the output is 0. So this is a particular kind of neural net unit called perceptron, which is a very sexy name because they had very sexy names in the 50s.
They did.
When this was first developed. All right. So this whole neuron concept gets boiled down to something much simpler, which is just a linear sum followed by a thresholding operation. All right. So it's worth kind of thinking, what sort of things can networks of these kinds of units compute? So let's see if we can figure some of those things out.